All right, we're gonna do this problem called Borris and his amazing haircut. So this question is cool. You can take a look at it, read it, and I'm just gonna get into it right now. I'm gonna code it to you. So basically, for this question, I'm just gonna present the solution. I sort of want to have quicker videos, not too long. Um, you basically the idea here is there are a lot of like other complicated solutions, but the simplest one that I found, you don't even need a monotonic stack, which the solution used. But it's basically the same idea. Um, but um, it's I actually have not tried if my solution works, but like it's the same thing. So we'll just cut it up and see if it works on camera or not. But basically, the idea here is I recommend playing around with the test cases like before you like actually watch the video. Like always play around with the test cases, right? Um, Once you play around the test cases, then the watching like the solution video will be more effective. So make sure you play around with all these test cases, know why they're true and why they're yes, and you probably might even be able to solve the problem. But the idea here is that when you get to a hair strand I, you need obviously. Okay, so actually, okay, first thing I'm going to do is without lots of generality, assume that. So basically, what this is saying is that all the hair strands that I want, which is B, are less than or equal to all the hair strands that I currently have, right? Like like for example, if you look at this test case, right, this is basically saying that all my hair strands are size one, and then after I go to like a haircut place, I suddenly want to have a hair size with size two. That makes no sense because when you go to a barber place, like you literally get a haircut, right? So that's your hair. So you don't need to be like competitive programmer to know that. It's just common sense, right? So just without loss of generality, assume that a sub I is greater than b sub I for all I. Now, now the solution is as follows. Basically, we know that when you start from a when you get to the ith hair you need a razor with value b sub I. The question is, can we? The question is, do we can we use another razor that already had the value b sub I or another that we used on hair J version. This is basically just saying, we might have used a razor that has the value that we want at a current hair strand before, right? So earlier when we were doing this process, so think of indices before I, that's why I say generally less than I, we might have used a razor that already has the value that we want right now. So the question is, we need to keep track of that because if we do have that razor, then we don't need to like remove another razor from the set of m razors that we're given. We can just use that razor again. So how do we know that? Well, this is from what you would do is you would to get this intuition sort of, you would play around with the test cases and you would realize that like just very easily, like even from the first test case, you would easily realize that like you need to keep track of if you use a razor, then keep track of the razor you used, right? And there's no point, for example, from simply doing test cases, you will notice easily that you must, must keep track of all the razors you've used so far. However, there is no point of keeping track of a razor if it doesn't work anymore. Now this idea is pretty vague. But the idea here is this, right? So let's say I have hair strand two. Let me use something better. Let's say I have hair strand like 8, 7, 6, and I want my hair to let's say uh 8, 7, 6. And then let's say obviously we need to assume this, so let's say 4, 6, I don't know, 7, and then let's say okay, yeah, let's say this, right? Let's say I'm given a razor 4. Let's say a razor 4 exists, right? Like basically what I'm saying is that like from just simply doing test cases, it's obvious that like you must keep track of all the razors you've used so far to keep track if you can use a razor again. And basically it's not using a razor again. I know it says like um you can only use each razor at most once, but what I mean by using a razor again, I mean that like if you for example, if you use a razor to satisfy this element and you need to use a razor to satisfy a future element which is over here, well then, as long as it doesn't mess up, as long as it doesn't make any of these hairs shorter than the desired hair, then it's fine. Then you can basically just use it over this entire segment. So effectively, you can just be using the razor again, even though it's basically like I'm basically like contradicting what this said. But that's basically what I mean. You can use a razor again, right? It's just that like okay, right? But this obviously requires you to keep track of the razors that you've used throughout the entire process. But you know that you don't want to keep track of a razor that doesn't work anymore. So if a razor makes any A value smaller than its current B value, then you don't want it. For example, in my first iteration, right, of the loop, I'm in an X1. Okay, I'm going to keep track of razor 4 because I obviously need to make this 4 for it to work. Then I go to X2, and then I'm like, shoot. Well, if I use 4 on this strand of hair, then I know that it's not going to work anymore. So there's no point of keeping track of 4 because it's not because even if I had some future um, value, so that was like 10, that needed to be 4, I couldn't even use it on this entire segment because it's going to spoil this hair, right? It's going to ruin this hair. So you couldn't even use it on this entire segment. So you don't keep track of it. So basically, I know this idea is vague, but it's basically just saying keep track of all the razors, and if it doesn't work anymore, basically, if that razor value is less, if that razor value is less than the B value, then it will ruin it. But you need to keep track of this for every single razor that you've used so far. So the question is, we know how the solution works now, right? Like, because then basically what we can do for each razor, we can just check. Like, for example, if I'm on like this razor on like let's say I get to razor like 5, right, and I need the value 2, then basically from all the razors that I kept track of, and these are you only keep track of working razors, right? So from all the razors that we've kept track of that work, then what we basically from that solution, all we need to do is just check for this guy, is a 2 inside that working razor, in the set of working razors, and if it is, then we can use it again, or you know what I mean by using it again now because I've already explained it. And if it isn't, well, then we need to decrease the frequency of how many two. That's more of a code thing. If it isn't, then it's straightforward with what we need to do. You'll see it in the code. But if it is, but the first thing is how do we check if a razor is if there is the desired value in all the working razors we've kept track of? Well, we can easily just use a tree set, right? Basically, what we can do is we can keep track of all the working razors and wait, do you need a tree set? Yeah, you keep track of all the working razors that you used so far. So this is basically keep track of all the working razors that you've used so far, and then when you get there to check if you can to check if um we can use a razor again for that I value. Basically, you can just do. if razor's stock contains a value we want for that strand, aka b value. And this will just work in log n time. So it will be efficient, right? The tree set is a binary search tree. This can be supported in log n time. So now the idea is that like how do we maintain the working razors tree set though? Like if I have a working razors of like let's say my working razors right now, and we don't even need more test cases, right? We can just move on. Let's say my working razors right now is arbitrarily like 1, 6, 5, 4. How do I maintain that? Like when I go to a index I have my a value and my b value. Basically, I want to basically invalidate a razor, aka throw it out of the tree set of working razors, if any one of these values is smaller than that b value. If it's smaller than that b value, then you have to throw it out, or it's going to make this shorter than that b value. In which case, it's impossible because you need to make sure all those a's are greater than or equal to it, and for this question to be possible at all times. So then the idea here is that you want to do that. And so the question is this fast enough? How do we do that then? The idea isn't too bad. I'm pretty sure what you can do here is you can just you can look at the first element, right? And basically, okay, here's what you need to do. If you're trying to see if there's any numbers, if you're trying to keep like a range of numbers, like some subset of these numbers, right? What you can do is if the smallest number is bigger than b, right? Then all these numbers work. All these numbers, if it replaces a, will still be bigger than b because the smallest number is bigger than b. So let's first check if the smallest number is bigger than b. If it's not, throw it out, and um, check if the next, which is sad. Well, it would have to be sorted, so that's why it's nice, right? And if it's not, throw it out. If it is, throw it out, and then go move on to the next one, and then check if 5 is smaller than b. If it's smaller than b, then throw it out. And then if 6 is bigger than b, then you know that it's good. And then if you know that's good, then you know everything else is good because it's a tree set and it's sort of in increasing order. So putting the working razors into a tree set, into this efficient binary search tree, basically, we can just we can easily just efficiently do operations. You know that this is like still like n log n up time complexity. It feels like it's O of n squared because we're checking we're checking like a tree set. We're like kind of going through a tree set and for like each razor. But think about it like this, right? In working razors, every like the worst complexity that you can think of, even if this is not possible, but the worst complexity you can think of is for each razor, it's going to be put into working razors, um, right? It will be put into working razors once, right? Every razor can be put into working razors once, right? Right? And then if it's put into working razor, we put it to put something into a tree set that takes log n, right? And then now it might be also removed from that tree set. So it can also be removed, which would be log n. And then we know that that's for one razor. There could be like a m of them, or technically this is m, right? There could be like m working razors because it says m, and so then we know that it's m log m, right? That entire thing in the entire code, it's gonna run in m log m. You know that, I mean, one. So just because you throw away one doesn't mean that a one won't appear again because there could be multiple ones in this set of m, right? So basically, yeah, but it doesn't really matter. We just show that like for each razor, you can remove, you add to it, and you also remove to it, and it's just m log m, type complexity, and so that it's not actually n squared. I think this is called like amortized complexity. Actually, yeah, switch it, amortized complexity. But yeah, that's basically what we're doing. And then um, yeah. So yeah, that's basically it. Because then you just go through each trend, so you know that like it's just gonna be plus some like linear factor, which is like O(n). Um, yeah, you go through each trend and you just check if it's working as yours. Now you can easily just code this. So that's what we're gonna do. But yeah, that's basically the solution. It's actually pretty straightforward. Um, I think sometimes you might have not got this solution because you might have felt that like that solution is n squared, but it's not because when you keep track of the working razors, each razor can be put into it. It will be taken. It can be removed out, right? Once you throw out a razor, you'll never put it in again. So you can. So basically, you apply log n, log m, whatever, right? A logarithmic factor on each razor, and there's a linear amount of razors, so the time complexity is log n. So you can confidently code this. Yeah. So some places use like a monotonic stack. Um, you don't really need to use them much. I mean, isn't this kind of basically the same thing? I mean, I don't know if it's fast. Is it faster? I don't know. All I know is that this works though. So yeah. And then there's some places that use segment tree, which I think is like very unnecessary. Also, like I know the idea of segment tree. I just don't know how to like implement it yet. Um, but yeah, segment tree is not. I don't think you don't really need it. Although I did think of like finding the minimum and maximum in a range and doing it like that. But obviously that requires heavier implementation than just keeping a running treeset, right, and applying a few operations on it. So for each of the razors, I'm gonna keep track of it um, as a hash map. Yeah, because I want to know. Yeah, yeah. If I'm not filming, I'll be kind of annoyed. Okay. Actually, I wouldn't be annoyed. It wouldn't really matter to be honest. 'Cause really. I like actually like doing input, even though like I know like you can copy and paste it somewhere. Like I mean, I know that like I'm very aware of that, but like I don't know, it's just type it. Like, I don't know. I like it. I like doing it. So it's kind of fun to just like brag about like being that you've typed like something like 1,000 times. I've not done 1,000 problems, so Borris has definitely no more than 1,000. Okay, off topic, but yeah, we're doing input stuff, so not too interesting right now. Although I just said it was kind of fun. I'm contradicting myself again. Okay. I typed it. Oh, we'll type a little faster. Okay, if I type a little faster, mistakes. Yeah, like that. Um, Maybe you could just copy paste and take variable for that's it. Okay. I feel like mom's gonna call me and say I should be doing my school homework right now. So I might be pausing to do so. I'm not really talking because I'm not really doing anything substantial right now. Is the size of a razor gonna be big? Yeah, dang it. And it's using a hash map. Oh shoot. Yeah, that's why Ripple is slow because this is obviously right. Oh wait, am I dumb? Yeah, like kind of stupid. Never mind. Yeah, I got a little humbled by that. Wait, no, razors I put the razor. This one. We maintain a frequency in the hash map, right? Basic stuff. Right now we can actually do the problem. First thing I want to do is just check if this question is stupid first. What I mean by that, obviously, like you can't one can't. Um, but I think this question is also easier if you just literally think of it as like a real life problem, rather than like trying to like do some generalizations from like segment L to R. No, like it's just a barber. Like it's literally like actually accurate. It's kind of actually a pretty good like connection. Not gonna lie. Whatever type of problem this is, the Asher's question. Yeah. Uh, or actually, I've got a plan, you don't know. Keep this to myself. I've got a plan, you don't know. Okay, so we print no. And then afterwards, we need to actually do some stuff. We need to track. All we need is working rules. I'm just gonna call it working. So I'm kind of lazy. First thing I want to do is that like, if it's already good, let me not look at it. That is if the hair trend is the same. Okay, so obviously it's not good. So basically, what you need to be doing is you need to go through. You need to see if you can use something again. So go through working. Um, Pick I think the one that I want. Yeah, no, it's full. It's working. Um, well, if it contains the one that you want, then just continue. If you get satisfied. Wait, if it contains the one that you want, then yeah, continue. And we're assuming that it doesn't contain the one that you want. Oh wait, you need to. Or we think we need to invalidate this. Well, the first element, because this is sorted, well, this is less than hairstring that we want. So we need to maintain working. Shoot, I want to actually. I don't want to have to keep calling. I have to call. Okay, so we need to maintain. First, let's maintain. Because like we can't use it for this one if it doesn't. It messes up the string. Yeah, maintain working. Sure. We did. This is how we maintain it. That should work. And then we've maintained it. We can just check if it's contained or if it's equal. Okay. Now, if it's not contained, then if this is not to get what we want, if it's well, here's the thing: we would have already broke. So if we get to this point of the loop, but I also do this though. So it's not else users dot most put this and then yeah, and then just that yeah, because we're gonna use it. But if we use if videos, if it's there, then we can just add it to working and just say that count of that is less. This should be it, right? T. E. Oh, why is it only why is it only why is it only four? Should be more than four? Why is it only printing four? I mean, the first four are right. The heck? Surrounding surfaces one. What? So only print out four? Oh, weird. Why? Oh, dumb. Some little debugging. I feel like this is more like I don't have to debug this heavily. It will be more of a light debug. Yes, no, yes, no, yes. Oh, it's just alternates. Um, I don't know. I don't want to get excited. It's like, I've done that several times. I feel. Cool. Alright, that's it. Cool problem.